So we are cooling it. That's why otherwise we could have just gone straight back to the tank. Bear in mind that all of the charge pump flow is coming out of the motor case at this point in time. You'll see that in just a minute. All of it. All right. So that shows us the case drain line in operation. Now we move on to the problem with the oil loss. As you can see here, we're short of a gallon coming out of the pump. We're short of a gallon coming out of the motor. So I've got 30 GPM, 1 gallon leaking, 29 in there, 28 out the other side, and I'm going to have to replace this oil, otherwise the loop is going to run out of oil. So the charge pump's next job is to replenish the oil in the low pressure side of the loop. So clearly what you can see here is, if I lose a gallon in the pump and a gallon in the motor, that's 2 gallons. I have a 2 gallon a minute deficit in my loop. So what I want the charge pump to do is, even though the charge pump flow is, let's say, 10 gallons per minute, of the 10, I want it to put 2 back, so it remains full at all times. So let's see how that works. So here you go. The charge pump is putting that oil back. You can see through the charge check valve now, it's putting that oil that I lost due to high pressure and lubrication back into the loop. So let's just say it's a 10 gallon minute charge pump. Let's say the leakage in the pump and the motor was 2 GPM. That means there's 8 GPM going out through the charge pressure relief valve and 2 going into the loop. As the system ages and the wear increases, obviously, if I leak 2 in the pump and 2 in the motor, that's a 4 gallon a minute deficit in the loop. The charge pump puts back the 4, and 6 goes across the charge pressure relief valve. That's the charge pump's job. All right, now folks, just let me pause over here for a minute. If the idle speed of a diesel engine is 25% of the high idle speed, which is probably just about right, and if the flow out of a hydraulic pump is proportional to the speed at which it runs at, if this is a 10 gallon minute charge pump at high idle, it's going to be a 2.5 gallon minute charge pump at low idle. So try to do the math. If I'm leaking 2 gallons a minute in the pump, let's say the operator's decided to figure out, I'm going to run this thing. Let me give you a case history. The operator was taking a blast hole drill from one level in a mine to the next level down, meaning he was going to go over the side, and drive down to the next level down at quite an angle. Well, if you've got a Detroit engine or a Cummins engine or Cat engine running at full tilt, well, naturally when you go downhill, you're going to throttle back. That's the inclination, is to throttle back, because it's sort of scary. You're taking this monstrous drill rig down a hill, so the operator may throttle back. Let's just say the operator can throttle back. Now, go figure this out. If I drop down to low idle on my engine, and I'm leaking out of my pump 2 and out of my motor 2, and if my low idle flow is 2.5, can you see what's just about to happen to this machine? It's going to run away. And you better hope and pray that the brake system on this machine can hold it. Hope and pray. And that's the problem when we let the operator use his or her discretion as to what determines the ground speed of the machine. Sometimes it's not even a good idea to make RPM a discretionary. In other words, I start my machine, it runs on idle, I hit a switch, it goes up to whatever, full RPM, and then you run it like that for the day. But it's not discretionary. So, sometimes that's prudent. I don't know. All right, so now we've seen what happens when we are leaking in our system. So let me just do that again. You can see the charge pump is now replacing the leakage. That's its job, so the loop remains full at all times. All right, next slide. As you can see, I'm going to now start the machine and run continuous operation. The charge pump, as you can see, is replenishing the loop coming through the check valve, that 2 GPM, and I've now gone in forward, and let's go in reverse. We said reverse is a mirror image of forward. So you see the same thing, except now the charge pump is putting the oil back through the other charge check valve, and I'm now going in reverse. All right, now let's see what happens when we stall the hydraulic motor. Locked up the hydraulic motor, you can see the oil coming across the main pressure relief valve to the opposite side of the loop. No oil in a closed loop system is allowed out of the loop. In other words, you can't drive another circuit off charge pump flow or main pump flow. You can't do that because this is a balanced circuit. Now you can release a brake. You can use charge pressure to release a brake. Like let's say you've got a multiple disc brake on a machine and you want to release it. In fact, sometimes it's built-in safety. In other words, if I use my charge pressure to release a multiple disc brake on a machine and I lose charge pressure or I lose my system, the brakes will automatically apply because I don't have charge pressure to release the brake. So that would be a safety benefit like you'd see on a snow grooming equipment and that kind of thing. Now let me show you. What you've seen here, folks, is you've seen this circuit working without the ability to cool the loop outside of normal leakage in the pump and the motor. Let me show you how clever the engineers got when they said, okay, let's do this. We are now bringing in 10 gallons, let's say, of clean cool oil. We're putting 2 back in the loop and we're taking 8 and just dumping it straight out of the circuit. Let's not do that. Let's make it so that I can circulate all of the charge pump flow in and out of the circuit while it's running. So let me introduce you to that circuit. Oh, sorry, let me just show you what, this is what a towing bypass valve does. So if you're towing a machine, well, first of all, let's start there. If you don't have a towing bypass valve, don't even think about moving the machine. There's been a lot of very, very unhappy campers because they got a machine stuck that's at a hydrostatic drive where you can't disconnect, which would be a bad idea in design anyway. And what they do is they hook it onto it with a D8, some dozer, and then they'll just pull it. You can kiss your transmission goodbye if you do that. It's going to trash it. So you don't want to do that. But the next thing you want to be careful of is the manufacturer, if it's got a towing bypass valve, will give you 2 precautionary statements. 1, only tow, don't tow at more than 3 to 5 miles an hour. Well, that's probably because it's a piece of construction equipment which looks really bad going down a freeway at 100 miles an hour while it's being towed. So 3 to 5 miles an hour is a safety thing. And then the other thing they might add is don't go more than 500 feet. The reason why they're telling you that, to go, no, don't go more than 500 feet, is because the charge pump is not running. And you've got high pressure, you're creating resistance across this valve, which means you're leaking internally, but you're not putting the oil back. So it's eventually going to run out of oil. And that's a bad news. So you got to be really, really careful that you obey the manufacturer. And never tow with a cable or a chain. Nothing that can recoil. The problem, folks, there's been a lot of people that got hurt because what they'll do is as soon as they disconnect the hydrostatic transmission, and let's say they're hooking it onto a towing vehicle with a cable or a chain, and it's a little downhill. As soon as they disconnect the hydrostatic, it's done. It's going to run away. These folks are going to understand the whole concept of hydrostatic braking, and this is all by default. This is not by design. This thing. I was doing an incident investigation, and I sat at my computer, and I didn't target 100. I just started writing down the number of reasons why you'd lose the braking on a hydrostatic transmission, and I have a page with 100 reasons on it. So it's very, very important to understand what it's all about. All right, so let's move now to hot oil shuttle. I've now introduced the hot oil shuttle valve, and now you have a complete heavy-duty transmission. Objective: instead of only replacing the leakage, replace the full capacity of the charge pump. What you're going to notice, though, is this. Excuse me. If I leak a gallon in the pump and a gallon in the motor, that means I've got a 2 GPM deficit in the loop. So ask yourself this question. How is it possible to put 10 in if you can only fit 2 into the loop? Because when I start it up here in a minute, you're going to see the charge pressure relief valve is not going to open anymore because it's a higher resistance than the charge pressure relief valve at the motor. Clearly what's going to happen is because the charge pump flow can no longer go through the charge pressure relief valve, all of it is going to circulate back into the loop. But since I can only fit 2 of the 10 in, it's going to cause 8 to be forced out of the motor through the hot oil shuttle valve. So in other words, it's going to say, hey, I'm here before you, so you push 8 out through the hot oil shuttle valve, and that's how it circulates in and out. Let me show you. So here's 350 psi. That's your charge pressure in neutral. All right? So that means you've got equal pressure on both sides of your hot oil shuttle valve. All right? Now, let's go to the next circuit. Now when I select forward, I'm going to immediately engage the hot oil shuttle valve. There it goes, which you can see clearly has now joined the low pressure side of the loop to the second charge pressure relief valve, which negates the first charge pressure relief valve at the charge pump only because they're in parallel and only because the charge pressure relief valve at the motor is set 50 psi lower than the charge pressure relief valve at the pump. So now you can see what's going to happen. If the charge pump flows 10 GPM, all 10 is going to come in through the check valve, all 10. As I said, of the 10, I can only fit 2. So what do you do with the other 8? Well, if you look at the motor circuit, you'll see coming out of the motor, which may be 40, 50, 60 gallons a minute, 8 of it is going to be forced up through the shuttle valve and out through the charge pressure relief valve. So it's going to push that 8 out. And that's how it's going to work. So let's see that again. I've activated my shuttle valve on the high pressure side. It's negated my charge pressure relief valve, the neutral, and it's introduced my cooling and filtering system to the loop. And as I've said, it's not preset. It can't be preset, folks. This is a setting that the mechanic has to make. If I put a new pump, a new motor, or a new pump and motor on the machine, my first responsibility is to make sure the charge pressure is set at charge pressure recommended by the manufacturer plus case pressure. Then I have to cycle forward and reverse and make sure on my charge pressure gauge I'm dropping 30 to 50 psi. And if it surges, in other words, if it goes down from 350 down to, let's say, 330 or 300 and comes back, it's not working. It's got to be a definitive drop from 350 to 300. Definitive drop. So there's my hot oil shuttle valve in full swing, taking care of business. Full charge pump flow through the charge check valve, and that the 2 gallons a minute, 1 gallon a minute leak into the pump, 1 in the motor, and the other 8 leaving through the hot oil shuttle valve. That system is working correctly, and that system will run relatively cool. All right, so what I'm going to do here is, just so for those folks who are not totally familiar with the layout of a hydrostatic transmission, I'm going to use our VCLS 300 to show you exactly what I've really just covered in our presentation. So what you're looking at here is a 2-in-1 trainer. The rear end is full hydrostatic drive, and it's a light-duty transmission for good reason, because this can run on a 115-volt circuit. The front end has got the same steering as any articulated machine, meaning it's got a steering orbital valve, it's got cross-port reliefs, it's got priority flow divider, and so basically we decided to just make this a 2-in-1 trainer. So right now we got the controls over here, the forward reverse control lever there. We got a charge pressure gauge here. We got an oil temperature gauge, and this thing has full fault capability. One thing that we are very good at doing is creating wear in components seamlessly, meaning that, and it's usually done via a computer on board the trainer. So we can make the pump wear out, we can make the cross-port relief valves wear out, whatever the case may be, in real time. Anyway, that's beside the point. Let's get back to how this thing works. What we did here, because some students have difficulty trying to figure out what is actually happening when I move forward reverse control lever backwards and forwards? What's actually happening in the unit itself? Well, to make that really clear, what we do is we buy two identical pumps and we take one and we cut it away in amazing detail. Then we put it just above the main pump and we link them together so they operate in concert. In other words, if I move the forward reverse control lever, I'm not only operating my main pump, which is turning the wheels, but I'm also operating the pump above. So not only can the student see how the swash plate is moving and going over center, but I can also rotate it's an axial piston pump, so I can rotate it and I can see how, when I go over center, it causes the flow to reverse. It also has a transparent charge pump, which is a Geroda type, which most are. If you look at any transmission, Denison, Rexroth, Sauer Danfoss, most of the charge pumps are Geroda or generated rotor design. So you've got your charge pump here. You can also see your little charge check valve in here, or charge pressure relief valve. And then you've got here on either side, you've got your high pressure valves with your charge check valves. All right. So basically, these are pretty much fixed from the factory. So a lot of these heavy duty transmissions, your main pressure relief valves are non-adjustable. They are fixed. And usually if you take the cartridge out, if it's fixed, you'll be able to read the pressure setting of the valve either on the side of the valve, or it'll be like a number stamped into the end cap of the valve. So if it's, for example, it's got a 50 stamped into the end cap, just add 2 zeros on the end, and it's a 5,000 PSI relief valve typically. We've also got dual high torque, low speed motors here. And for safety, these things are not connected. So we don't want a student to hold on to this and then another student, because students are adventurous, and then of course it wraps their coveralls up in it, and that's a problem. So they'll spin, but they're not connected to the shaft for safety purposes. So we can connect this up in series or parallel so that you can demonstrate high speed and high torque. And then of course, because the main pressure relief valves are not adjustable here, we overrode them with another set of cross-port relief valves, which are adjustable so that the students can see what happens when they make the adjustments on the valves. The other thing that's unique is when you're testing a hydrostatic drive, testing is a whole different ball game on hydrostatics, especially when you're looking for wear in pumps and motors. So one of the things that's important is to always test in the direction it spends most of its time in. And that applies to so many components, like cylinders, for example. You see so much stuff on the internet about testing hydraulic cylinders. So there's that one particular test where they plug the live end port and then they put pressure in the closed end port. And if it's leaking, it'll regen out. That is probably the most dangerous thing you could ever possibly do. The reason why that test is flawed is because if the cylinder has a dual seal system in it, and the seal on the live end is not leaking, it doesn't work. The test is worthless. So what we're saying is that when you test a hydraulic cylinder, always test in the opposite direction to which you're drifting. So if this hydrostatic transmission was driving a drill rig, for example, it's going to spend 95 to 98% of its life turning in one direction only, and the opposite direction will only be when you're breaking a pipe loose. So you always test in the normal direction. The beauty of this particular type of flow meter is that it reads going both. It's an analog flow meter, but it reads going in both directions. So I can read the oil on this flow meter. I can either go forward or I go reverse. One of the most difficult things to do is to put a flow meter in the line from a pump or a motor. So in order to mitigate that, some years ago, and I can share this with the instructors because I would highly encourage instructors to teach micro-leak testing. So let me just give you a little bit of background there. I saw when I started out that, first and foremost, and I'm going to say this with the greatest amount of respect, hydraulic systems are not designed to facilitate any type of maintenance. And so let me just say respectfully, the last thing on an engineer's mind when an engineer designs a hydraulic system is the maintenance person. Because unless you've been out there maintaining and troubleshooting, you don't really understand the hardships. So, having said that, I did a study. Well, for 10 years, I studied leakage rates in hydraulic components due to wear. And I found that many of the components you see cannot be tested with a flow meter. You can't test a directional control valve with a conventional flow meter. You can't test pressure controls. You can't test check valves, nothing. So what I decided to do was to come up with a way to field test components using micro leaks. Well, in other words, we're looking for micro leaks. A pressure relief valve is micro leak. You're not looking for 10 gallons a minute leaking from a relief valve. You're looking for fractional flow. And the only way to find fractional flow is with a micro leak. So this unit has a micro leak. This is a micro leak test pump on this unit to teach students how to test cross-port relief valves, test check valves, etc. in the circuit. But the beauty of micro leak testing has got to be safety. You can't beat it on the safety. Meaning this, you can test 98% of the components in any hydraulic system without starting the engine. Well, think about that from a safety point of view. I've seen people take 994 cat loaders, raise the bucket in the air to try to check for leakage on one of the lift cylinders. It's the most dangerous thing in the world. And it's not because it's a 994 it's dangerous, it's because it's just a dangerous procedure. Then we talk about using thermal imaging. Sorry, I'm just not a believer in any kind of thermal imaging for troubleshooting. And here's why. I've got a check valve and a relief valve in the same body, and it's hot. Which is leaking? Which is leaking? I don't know. If you take a direct control valve, for example, on a front-end loader that's got an anti-cavitation valve and it's hot, is it the spool and the bore that's leaking, or is it the cartridge valve? And if it's a 10-section valve on a crane, why would you take the whole thing out? It's pointless. Micro leak testing, which I invented more than 20 years ago, will revolutionize the troubleshooting industry because I can actually micro leak test this pump. I can actually micro leak test these motors. So where you can't use a flow meter because it's first of all almost impossible to get it in, and who's going to have all the fittings, but it's also going to be a very challenging job to read what we need to read while the pump is running. Take load sensing pumps. I've had several complaints in the last little while of people that said, well, we started the system and I have no flow on through the flow meter, and I know for definite I have flow in my system. Well, actually, what kind of pump are you testing? A load sensing. You don't have any flow. You're in neutral, you don't have any flow. In other words, they assume that the pump should be flowing all the time. So where you get into problems is with over-center pumps, with pressure compensator pumps, with load sensing pumps is if the student doesn't understand that there is no flow in neutral, then that's going to be problematic from the point of view of troubleshooting. So micro leak testing is completely revolutionary because it allows me to check almost every valve in my system for leakage. I would highly recommend that instructors advise students that when a manufacturer says, and many do unfortunately, disassemble and inspect in the field. How many students are actually trained or technicians are trained to disassemble and inspect anything? And then you say, well, disassemble and inspect this valve here in this cross-port relief valve in this transmission. Well, fine, I can take it out, but I can't disassemble it. You can't take it apart. So what does disassemble and inspect amount to? We've got to be really careful about how we interpret that. Am I competent or qualified to do that? It's a whole different ball game. So these types of transmissions are very, very simple, and yet to the uneducated or ignorant person, they're extremely complex. And one of the biggest problems we have is we need to have a subject completely separate subject called post-catastrophic failure startup. In other words, I want you to imagine that I've blown the hydraulic pump, I failed catastrophically on my pump, and I'm going to install, usually what they'll do is they install a new pump. It would be wise to install everything new, including the high pressure lines. In other words, if I blow a hydraulic pump on a catastrophic failure, not a normal wear failure, catastrophic failure, why would you ever put the closed loop back? I'm not talking about replacing the case drain lines. Why would you put the closed loop? I'm talking about flexible. I'm not talking about steel lines right now. I'm talking about flexible. Why would you ever put them back? Because if you've had fragmented inside your pump and you've broken bearings or broken pistons, which are as hard as glass, why wouldn't one of those things go on and get stuck in the side of a piece of hose? It just deflected off something, coming around a corner. One piece, that's all you need. You put a new pump and a new motor on there and you fire it up, and that piece dislodges as you have pressure spikes in your system, and it goes through it's done again. I have been to machine after machine after machine where they started out with a catastrophic failure, and then they went through, in one particular instance, 7 pumps and 8 motors they went through, but they could not restart. They kept repeating the failure. What they did out of desperation is they started putting high pressure filters in the loop, which is the worst thing you can possibly do. Because high pressures in a closed filters in a closed loop system serve no purpose. In fact, in my opinion, they create more problems. Because first and foremost, if you want a filter going in both directions, you have to have 4 filters. There's this myth that if I blow the pump on a catastrophic failure that I'll be able to keep the motor. Well, that's a myth. In other words, at the point in time you blew the pump, how did you know that high pressure filter in that line wasn't in bypass momentarily? It was a cold start failure, and I was in bypass. There is no assurance. Second problem, it's halfway, let's say, between the pump and the motor, which means when I start my new system, I'm going to run the oil backwards through a line that is potentially contaminated. Now, folks, if we shoot projectiles through lines to clean them of debris, it's not going to work. In other words, projectiles are recommended for brand new hydraulic hose assemblies. But once the hose has got oil in it, projectiles are useless. In other words, unless you wind up with virgin rubber, you've still got an oil film in the hose, and the oil film will hold contaminants. Besides, if you fire a projectile through a line that's got shrapnel in it, it's going to push the shrapnel into the hoses. It's going to leave pieces of the projectile behind. And then one of the recommendations when using projectiles is that you always shoot 2 through. 1, after you cut the hose, and 2, after you've crimped the fitting. Why? Because when you crimp a fitting, it leaves a little dent in the hose inside. So if you blow a projectile through there and it gets to that point, it's going to drive it down, the contaminants down into that little, let's say, potentially do this, because it could have an edge, right? And it's going to drive the contaminants into there, and you're going to think, well, this is going to be clean. Be very careful of those kinds of things. I'm not saying it's impossible. All I'm saying is that it's not always the right solution. So if I have a catastrophic failure on a pump or a motor, the smart way forward is to replace pump, motor, and all high-pressure lines, flexible. I mean, you're talking about $50,000 transmission and maybe $350 worth of hoses. It just doesn't make sense to leave the old hoses in. Now, what I cover in the articles I've written about post-catastrophic failure startup procedures also covers steel lines. Because if you're out in the field and you've got steel lines on a machine, like on an excavator, I'm sorry, folks, you're not going to be replacing every single line on that piece of equipment. Let's be realistic. So what we do in that case is we replace the pump, and yes, we replace the motor, but what you do is you loop the lines at the motor. And I don't care if they split flange, it doesn't matter. We've got all the stuff to do that with. In other words, all you have to do is loop a line so that the lines are joined, and then go and put a 0 to 1000 psi filter at the inlet port of the pump. What we call is a slave filter for startup. It only needs to be 1000 psi because you're not going to run higher than charge pressure when you start it. What you do then is you start it up, considering now you've got all these steel lines that potentially got contaminants in them, and you go to full throttle, full swash plate angle forward, and you run flow through from the new pump, bypassing your new motor with that line you put in, and then back through the filter, and you do that for about 30 to 45 minutes. And then you do it in reverse. Now, the reason why you want to do it in reverse is because if you've got any kind of fitting like manufacturers will make for hydrostatic drives, they'll make a T, an elbow. But they may make it out of a piece of steel, so they drill into the steel from one side, and then they'll drill in the other side. But when you drill in, it's going to leave on the other side of it. It's going to leave where you come in, the two holes come together. There'll be little wells in there. Now, every fitting is a centrifugal filter. So if I've got oil coming at high velocity around a corner and it throws the dirt into the corners, it's not going to come out unless I go backwards. So the prudent thing to do is to go in reverse. So when I think about it, okay, so let's talk about track record. In other words, this is what I've personally done in the field. My repeat failure rate is less than 1% in my career, which spans 20 in the field, on post-catastrophic failure startup. So obviously it has some meaning. And just to make my point very clear, years ago, a drilling company brought 3 hydrostatics off one machine and 2 open loops to me that had failed catastrophically. They dropped them off, and they went and got right here in Salt Lake City, they went and got a local, they stayed in a hotel. 3 days later, they came and picked them up. I took them into a little room, and I gave them this little speech. This is a long time ago. This is when I used to actually work for a living. I gave them a little presentation on how to start it up. And I always jokingly say, I can just see them already driving out of Salt Lake City on the way to Nevada saying, did you listen to that South African? Are we going to do all that stupid stuff? Folks, I gave them a bill for $9,500. 3 days later, that same vehicle reversed up to the door, and I took another $9,500 from them. And the gentleman who brought it in said to me, he said, I'll tell you what, this time we'll actually do what you recommended. I rest my case. So this stuff can eat you up alive, or we can train people how to do the job properly and get a good, satisfactory outcome. And that's the smart way forward. All right, so I'm going to pause again for anybody that has any comments or questions at this point in time.
So I've got one here, Rory, that says, couldn't the debris cut the line?
Excuse me, couldn't the debris do what?
Cut the line?
Oh, certainly. You mean all the way through?
Not sure. That's all it said.
Certainly, the debris can certainly cut the line. That's a very good point. It can damage the line. I mean, this stuff is sharp. It's shrapnel. I mean, you've broken up a bearing for all intents and purposes. When I say bearing, pistons and bearings, the pistons in these pumps are as hard as the bearing. So yeah, absolutely, it can cut it. I don't believe it'll cut it all the way through. You know, everything's plausible, but certainly it could cut the line. Good point.
Cool. Got another one here that says, is the closed loop PowerPoint with animations for sale?
Oh, everything's for sale. If you buy that, I'll throw in my firstborn son free of charge. These things are all available, folks. Just need to go through our dealer and we'll take care of you. Some of the communication stuff we'll deal with, but I think the best way to go through the communications channel here, unless it's going to the Fluid Power Training Academy, because just for the record, this course, this entire presentation will be online in about a week, 2 weeks from now at the Fluid Power Academy. So we are constantly uploading to help instructors, because what we're trying to do is we're trying to help instructors. And by the way, for the instructors that are out there looking at this, and we certainly appreciate your time, but also remember that about 4 or 5 years ago, we started complimentary training for taxpayer-funded colleges. You know, we're trying to help. Our objective here is, I'm a teacher. This business is here by pure default, by pure accident. I'm not a businessman, that's pretty obvious. But I'm a teacher. I started building these simulators in my garage over 30 years ago, and it became what it is today. And thanks to some really, really smart people, we continue to develop these brilliant products. However, one of the things that I saw as a problem was a lot of the diesel. I feel really bad for a lot of the schools I went to, because what they'll do is the diesel mechanics, because they do fuel systems and oil lubrication systems, they'll automatically shift them over to hydraulics, and it doesn't always work. And so they get this extra load, but they don't have help. So here's what we can do to help. Not only do we offer all of our workshops to taxpayer-funded schools are complimentary. So in our first year, that's 4 years ago, we had 18 teachers here, and it's been very successful. So please, all of you out there that have worked for taxpayer-funded schools, our training is complimentary. We want what's best for our country, what's best for our students, and we want our students to get good jobs. So just to give you an idea, as a troubleshooter, for the years that I did nothing but troubleshoot, I was charging $120 an hour. Now, I'm not saying everybody that graduates from school is going to go out and earn 120 bucks an hour. All I'm saying is this: for anybody to earn 120 bucks an hour, you have to have a rare occupation. Well, how is it in the United States of America possible for a competent fluid power technician to be a rare occupation? There should be a dime a dozen, just like we have brilliant diesel and automotive mechanics. Brilliant. I mean, you look at some of these hot rod shows. These folks are absolutely brilliant. But how can we be so short of competent fluid power technicians? And so what we are trying to do is give back, meaning if we can help instructors get up to speed, we're going to help students get good jobs. And they'll be able to keep our manufacturing plants running, and the jobs will stay right where they are right now, or hopefully here in our country. So it's basically a win-win for everybody. So everything you see here is available to help you, and we will help any which way we can. The online training is going to be for the benefit of those instructors, because like I work with schools that have instructors working 3 shifts. They're not going to, when are they going to go to school? So what they can do is we're making these workshops so the instructor can either put our presentation on the screen. We call it iLearn. The instructor can put it on the screen and play it, but the student and the instructor will be watching it together. What the instructor is doing, and the students may not know this, is learning from us. After the instructor has gone through it 2 or 3 times, and in my case, if anybody like me, it'll be 10 times, then you turn it off and you do the narration. So the idea is to let instructors take little snippets of hydraulics, like even a counterbalance valve. If you don't know how counterbalance valves work, go there to the site. It's not there yet. It'll be there. But a snippet. How does a counterbalance valve work? So what we're trying to do is help instructors that have got such a massive workload. And just for the record, we write our own textbooks. We produce all our own material. We produce every one of our own slides. We produce our own animations. So what we're saying is everything is cohesive. You don't have to start jumping around. So like on hydrostatic dryers, what you just saw is generic, cohesive, and it works for everything. So So to that end, I think, hopefully that has answered anybody's question about the availability of information.
Good, thank you, Rory. I do have one bit of, I don't know if it's necessary, but the question previously about couldn't debris cut the line, you clarified as you're pushing the projectile. Does that fall in line with what you already answered there? Or?
Okay, I'm just a little, yeah, I think if you've got debris in the line, and I'm assuming that's exactly what it's all about, and you run a projectile, because the projectiles are really tight. You know, you blow them through with compressed air. I don't see any reason, that's a very good point, why you couldn't go, let's say, across a flat surface that's got a jagged edge on the other side and drive it into the hose and potentially cut it. I think that's a really good point.
Good deal. It looks like that's all the questions that we've got coming in right now. Unless I'm missing one. So you can go ahead and continue, or if you're all done, then we can walk through how to get a certificate for this and break for lunch. What would you like?
No, well, I'm pretty much done, unless anybody's got any specifics about, let's say, troubleshooting or any troubleshooting questions, any specific questions, and we're pretty much there.
Good deal. I'll watch for those here. I'm going to cut away. If you'll just stand by there, just to walk people through that process again of getting there.
Can we put that slide up? Oh, the slide up with the web addresses on it.
Yes, if you want to share that with me, I can go ahead and pull that up as well. So the
all right.
Anyway, again, here's the button to request the certificate. It's right back here in the section where we've got all of the sessions listed. Right after we're finished here in the next 7 minutes, we got a virtual trade show during the next hour. Come in here and check out more about the Fluid Power Training Institute products, some of the things that we've seen in the course of this, as well as things from the other partners who have helped support this event. Let me switch back over here to Rory's. Of course, we've got quite a bit of information on the Fluid Power Training Institute on our website, but if you want to go straight to the source, fpti.org. I'm going to get that just about ready there. Okay. Yeah, so the fluidpoweracademy.com or fpti.org. Those are going to be your most comprehensive sources to take a look at. We've got a comment here saying, fantastic session. Thank you so much. I got some emails in the middle of it saying, this is fantastic. Thank you for bringing in forward-thinking partners for education like this. So we really, really appreciate the time that you spent with us today, Rory. And I can't endorse Rory more. I can't endorse him enough. If you go to fpti.org, you'll also see that he's got workshops that people travel all over the country and even all over the world to come and attend 2 and 3 day workshops that go far more in depth than we're able to cover in this short amount of time. So be sure to take a look at that. Obviously, there's some challenges with that with COVID-19 at present, but that's not going to last forever. Anything you want to add, Rory, before we break for lunch?
Yeah, we do have a workshop, a trainer workshop coming up in August. So there's 2 practical. Is the practical still on? Yeah, practical and troubleshooting, again, 2 taxpayer-funded schools, complimentary. I'm also going to recommend that anybody that's got any inquiry about any of the equipment we've used here, please take those directly to DACTIC. DACTIC is one of the most qualified of our, we don't have many dealers, but DACTIC has done a tremendous job in getting to know our products and understanding our products. They've spent 2 weeks in our training program, and I highly recommend that those kinds of inquiries go directly to them. Anything to do with like training materials, etc., it's probably better to go through our communications on that. However, equipment-wise, we have if you go to our website or DACTIC's website, there you'll see everything we have. And hopefully in the future, we can feature other workshops with other types of equipment. So we look forward to working with you folks, and instructors, remember, we're here to help you get up to speed with this training, and we'll do whatever we can to help you get there. And we've got some amazing materials on every topic. We are also open to credentialing with schools. Schools and colleges, credentialing with them. That means that, for example, let's say you want your student to go away with not only certification from your school, but also certification from the Fluid Power Academy. Then you can have the student. Our standard is very high, though. And I'm not saying this to say that yours isn't. All I'm saying is we will not pencil whip it. So only students that really work really hard will be able to pass our tests. My point being that means that they will leave the college with not only certification from the college, but also certification, credentialing from the Fluid Power Academy. And we have a very, very good reputation in the industry as a whole, especially in the area of safety. So most companies will recognize that. So we're not affiliated with any organization. So I don't want to try to pretend that this is going to be a shoe-in. We set our own standards. We write our own books. So anybody that is interested in that can contact us as well about credentialing. So we're open to any way to improve a student's opportunity to get a good paying job.
Excellent. Thanks again, Rory.
Thanks, everybody.
Yeah, thank you. So we'll break for lunch right now, and go ahead and you can still, when you come back after lunch, be sure to check out the session that we've got with Darcy Weddle. He's going to be talking about gamified learning, which is particularly relevant right now when so many of you are having to teach long distance. So be sure to come back for that in an hour from now. That's going to be 2 o'clock Mountain Time, 1 o'clock Pacific. Thanks again, Rory. We'll talk to you guys soon.
Thanks for all your efforts, and thanks again for inviting us to this presentation.
For sure.
Be safe, folks. Stay out of harm's way.